We are now going to learn how the equilibrium constant, the magnitude of it, varies with different concentrations. Notice we're going to use our reaction between hydrogen and iodine to form hydrogen iodide. And the equilibrium expression is going to be Hi squared divided by hydrogen times iodine. Notice all the products as well as all the reactants are included in the equilibrium expression, and that is because they are all gases. Now, in this problem, we have all the equilibrium concentrations of all our reactants as well as our product. So this is a really simple problem in that we all have all the values that we need. And so all we need to do is to plug them into the equilibrium expression. I would like you to pause this video and try and calculate the equilibrium expression based on these values. Now, if you got a value of 173, you are correct. You would plug in the 0.770, which is the Hi concentration, and you'd square it, and then multiply by the concentration of iodine times the concentration of hydrogen times the concentration of iodine. Notice you're going to get this number right here, but because all these values we are dividing and multiplying have 3 sig fig, our answer is also going to have 3 sig fig, and that's why our answer has 3 sig fig here. Now I'd like you to look at this value and try and make an educated guess as to whether we have more of the reactants or if we have more of the products, or if we have about an equal amount of reactants and products. If you guessed that we have more of the products, you're right. We have a bigger numerator, which means that we have more of the products, and a smaller denominator, which means we have less of the reactants, and that's why our number is coming out as 173. We are usually comparing our numbers to 1, and so we see that 173 is much greater than 1, so we have more of the products than the reactants. Now we have 3 different scenarios, and you can try and figure out what those scenarios are going to be. In the scenario we just looked at, we have more of the products, so our K equilibrium was greater than 1. Notice here we have 3 moles of Hi, and we have only 1 mole each of hydrogen and iodine. So what we can see is that we have more moles of products than reactants. So our numerator is going to be much, much greater than our denominator. And so we're going to get a number that is greater than 1. Now let's look at this scenario. We have 1 mole of iodine and 1 mole of hydrogen and 1 mole of Hi. This doesn't usually happen in experiments, but it works for this illustration. 1 squared divided by 1 times 1 is going to be 1. And that's an ideal case where we have an equal amount of reactants and products. However, in the lab, we're going to have an approximately equal amount of reactants and products, and the equilibrium constant will approximately be equal to 1. The last scenario we're going to look at is where we have more of the reactants. Notice we have 3 moles of Hi and 3 moles of iodine, and only 1 mole of the product there. So what that tells you is that we have a smaller numerator and our denominator is way bigger. And so we have an equilibrium constant that is much less than 1. And so if we have an equilibrium constant that is less than 1, we can tell that we have more of the reactants. So in these scenarios, we can tell that the equilibrium favors the products if it's much greater than 1. We have an about equal amount of reactants and products if the equilibrium constant is about 1. And then we have the reactants being favored if our equilibrium constant is much less than 1.